What happens if small models begin to dominate the AI landscape? Executive summary. The past decade of AI progress was defined by ever larger models and hyperscale data centers consuming massive energy and water resources. Now a shift towards smaller, task-specific models is emerging, enabling efficient computation on distributed, regional, or even edge systems. This decentralization promises lower energy use, reduced environmental impact, and greater data sovereignty while broadening participation beyond tech giants. Hyperscale centers will still train giant foundation models, but smaller ones will handle fine-tuning and inference locally. The future of AI infrastructure will be a layered, sustainable, and democratized mesh of interconnected computing nodes rather than a few massive monoliths. Article for the past decade, the digital world has been quietly shaped by an arms race of scale. Every major advance in artificial intelligence, from natural language processing to image generation and multimodal reasoning, has depended on bigger models, running on bigger data centers. Companies like OpenAI, Google, and Meta have built vast hyperscale facilities filled with thousands of GPUs, consuming hundreds of megawatts of electricity and millions of gallons of cooling water each year. But as AI continues to evolve, a countertrend is emerging. Instead of one-size-fits-all foundation models with hundreds of billions of parameters, developers are turning to smaller, task-specific models that can perform well on specialized jobs using a fraction of the resources. This shift could have profound implications for how and where we build the physical infrastructure that powers AI. If small, efficient models become dominant, the entire geography and logic of computing infrastructure may change. The future might belong not to a handful of massive, centralized data centers, but to a diverse ecosystem of smaller, distributed ones. This essay explores why that change could happen, how it would reshape energy use, networking, and economics, and why hyperscale centers will still have a role to play even in a more decentralized world. 1. The age of giant models and giant data centers. Until recently, AI progress was defined by sheer scale. Each new generation of language or vision model was exponentially larger than the one before. GPT-3 had 175 billion parameters. GPT-4 is believed to have well over 1 trillion. These models demanded vast compute clusters and immense quantities of training data, so much that only a few hyperscale companies could afford to build them. That demand drove the construction of enormous facilities optimized for high-density computation. Custom-built GPU pods interconnected by ultra-fast InfiniBand networks, allowing thousands of processors to act in unison. Specialized cooling systems including immersion and evaporative cooling to dissipate extreme heat. Dedicated renewable energy contracts to offset the massive power draw. These centers can each consume as much electricity as a small city. Their very scale makes them efficient per computation, but also environmentally and geographically concentrated, creating local strain on energy and water resources. In short, big models required big machines, and big machines required big buildings. The centralization of AI was both a technical necessity and an economic strategy. 2. The emergence of smaller, specialized models. Now, however, the AI landscape is diversifying. A growing number of organizations are developing smaller, domain-specific models, systems designed for particular tasks rather than universal reasoning. These small models include distilled or fine-tuned versions of large models, such as OpenAI's O1 Mini or Meta's Llama 3.8b, lightweight transformer architectures trained for single-purpose tasks like summarization, classification, or translation, edge-optimized models that run on phones, vehicles, or IoT devices without relying on the cloud. They achieve impressive accuracy through specialization, fine-tuning, and contextual awareness rather than brute force scale. Many organizations now realize that a well-trained 5 billion parameter model can outperform a 100 billion parameter generalist for a narrow domain, and do so at a fraction of the cost. This evolution raises a pivotal question. If AI no longer requires massive monolithic training clusters, why should our data infrastructure remain so centralized? 3. Technical shifts that enable decentralization. A. Lower computational density. Smaller models need fewer GPUs, less memory, and less energy. They can be trained on clusters with tens, not thousands, of high-end accelerators. Inference, the process of running the model to generate answers, can often happen on standard CPUs or modest GPUs. This means compute no longer has to be concentrated in massive facilities. A small data center, or even an enterprise server room, could host multiple AI workloads effectively. B. Weaker interconnect dependencies. Large models rely on ultra-fast internal communication, hundreds of gigabits per second, between GPUs. Without this, training speed collapses. Smaller models don't require such tight synchronization. They can operate on loosely coupled systems, tolerating normal network latency between nodes. That makes geographic distribution technically feasible without crippling performance. C. Modular training and fine-tuning. Instead of training from scratch on global datasets, smaller models are fine-tuned on local data, regional languages, industry-specific documents, or proprietary information. That kind of data is often sensitive or private, and it's inefficient or legally risky to centralize it. Hosting local training in smaller regional data centers becomes not only viable, but desirable. 4. Environmental repercussions, smaller, greener, closer. The environmental calculus shifts dramatically in a world dominated by small models. A. Distributed power loads. Rather than a few hyperscale centers, each drawing 100 megawatts of power, imagine thousands of smaller facilities drawing 1 to 5 megawatts each. That distribution reduces the load on any single grid, smooths demand peaks, and allows each site to integrate local renewable energy sources, solar, wind, or microhydro. Microgrids and battery systems could make regional centers semi-autonomous, operating sustainably without requiring new high-voltage transmission lines. B. Reduced water and cooling needs. Smaller centers can use air cooling or closed-loop liquid systems that require little or no fresh water. In cooler climates, some could rely entirely on free air cooling for much of the year. By avoiding evaporative cooling towers, they would eliminate one of the most controversial aspects of hyperscale data centers: water withdrawal in drought-prone regions. C. Environmental justice and equity. Concentrating large data centers in a few regions creates local environmental and social strain, higher electricity prices, land use conflicts, and ecological disruption. A more distributed network could spread economic opportunity more evenly, bringing jobs, connectivity, and investment to smaller cities or rural areas while avoiding resource monopolization. 5. Network architecture in the small model era. The shift towards smaller models aligns naturally with federated and edge computing architectures. A. Federated learning. Federated learning allows multiple sites to train on local data and share only model updates, not raw data, with a central aggregator. Hospitals, for example, could collaboratively train a medical model without violating patient privacy laws. Each site contributes learning while keeping data on-premise. Smaller regional data centers are ideal for such federated nodes, forming a mesh of cooperative intelligence instead of a single monolithic AI brain. B. Edge inference. As models shrink, they can run directly on devices, smartphones, cameras, vehicles, or industrial sensors. These edge models handle immediate decisions locally, for example, detecting a safety hazard on a factory floor, while periodically syncing with regional or cloud models. This reduces latency, conserves bandwidth, and allows real-time responsiveness that centralized systems cannot match. C. Cooperative regional centers. Between the global cloud and the individual device lies the regional data center. It is small enough to be local, but powerful enough to serve thousands of users. These centers could act as middle nodes, caching data, serving AI inference requests, and coordinating local training tasks. The resulting architecture resembles a hierarchical neural network of data centers, an ecosystem of hubs and spokes optimized for latency, energy, and resilience. 6. Economic and strategic implications. A. Lower barriers to entry. If training and hosting AI no longer require billion-dollar facilities, far more organizations can participate. Startups, universities, and government labs could train or fine-tune models in-house, stimulating innovation outside the current tech oligopoly. B. Regional autonomy and data sovereignty. Countries concerned about data privacy or digital sovereignty could host their own AI models domestically. Smaller, distributed data centers make it feasible to maintain national AI infrastructure without relying on foreign cloud providers. This could reshape global digital power dynamics, making AI less centralized, not just technically, but geopolitically. C. Economic localization. Instead of clustering jobs and investments in a few hyperscale regions, distributed AI infrastructure could revitalize local economies, especially in areas with inexpensive renewable power or cooler climates suitable for efficient cooling. 7. The role of hyperscale centers in a small model world. It's important to stress that smaller models won't eliminate the need for large data centers entirely. The biggest models will still serve as foundation systems, massive general-purpose networks trained on enormous data sets. These will act as the brains from which smaller, specialized models are distilled. A. Foundation training. Training a trillion-parameter model still requires tightly integrated compute clusters. Only hyperscale centers can provide that kind of power density and networking. B. Distillation and deployment. Once trained, those large models can be distilled into smaller ones, essentially compressing their knowledge. These smaller models can then be deployed widely, from regional centers to personal devices. Thus, the AI ecosystem of the future will be tiered. 1. Hyperscale data centers for training and global coordination. 2. Regional centers for specialization and fine-tuning. 3. Edge and device-level compute for real-time inference. The result is not the death of the data center, but its evolution into a multi-layered organism. 8. New challenges of a distributed future. While decentralization brings clear advantages, it also introduces new complexities. A. Coordination and orchestration, managing thousands of small data centers, updating models, synchronizing data, maintaining consistency, is non-trivial. New orchestration frameworks will be needed to automate these tasks efficiently. B. Security and trust. More nodes mean more potential vulnerabilities. Distributed infrastructures must adopt strong encryption, zero-trust networking, and continuous monitoring to prevent compromise. C. Energy optimization. Across the network. Balancing workloads between sites based on real-time renewable energy availability will require AI-driven scheduling, effectively using AI to optimize the infrastructure that powers AI itself. D. Avoiding fragmentation. If every region trains its own models independently, interoperability could suffer. Standardization of model formats, APIs and training protocols will be essential to maintain a coherent AI ecosystem. 9. The broader environmental and societal outlook. The rise of smaller models offers a rare opportunity to make AI both more sustainable and more democratic. Lower embodied emissions. Smaller facilities require less concrete, steel, and equipment to build. Localized renewables. Distributed centers can tap into smaller-scale solar and wind projects, reducing transmission losses. Circular resource use. Waste heat from micro-data centers could be used to warm nearby buildings or greenhouses. Resilience. A network of smaller centers is inherently more fault-tolerant than a handful of megacenters. Privacy and ethics. Processing data locally enhances control and compliance with emerging data protection laws. Yet the transition must be guided carefully. Without coordination, decentralization could lead to inefficiencies or environmental duplication. The challenge is to design systems that combine local autonomy with global efficiency, the digital equivalent of a smart, adaptive ecosystem. 10. Conclusion. From monoliths to meshes. For much of the last decade, the story of AI infrastructure was one of consolidation and concentration. The logic was simple. The bigger the model, the bigger the data center. Centralization brought economies of scale, technical efficiency, and control, but also environmental strain and dependency on a few corporate players. Now, as smaller and more specialized models rise to prominence, that logic is starting to invert. When intelligence can be localized, fine-tuned, and distributed, computing itself can be decentralized. Data centers can shrink, multiply, and move closer to where data is generated and decisions are made. In that future, hyperscale facilities won't vanish. They'll anchor the system, providing the foundation models and global updates that feed a vast constellation of smaller nodes. But the overall topology of AI will look less like a pyramid and more like a web, interconnected, adaptive, and regionally diverse. The transition from giant monoliths to distributed meshes represents not just a technical evolution, but a philosophical one. It suggests a world where intelligence, human or artificial, is not concentrated in a few centers of power, but diffused across the network, woven into the fabric of cities, industries, and individual lives. That is the promise of the small model era, a more sustainable, resilient, and democratized AI infrastructure, one where computation happens everywhere and the benefits of intelligence belong to everyone.